Hello, welcome to Mustang Math. My name is Shoria, and today we'll be talking about Chinese Remainder Theorem. In today's lecture, you will learn what modular arithmetic is, how to solve problems with mod, and all about the Chinese Remainder Theorem. So let's take a look at the problem that we will explore today. A positive integer n is the smallest possible value that has a remainder of 1 when divided by 3, a remainder of 2 when divided by 5, a remainder of 3 when divided by 7, and a remainder of 4 when divided by 11. A positive integer m is the smallest possible value that has a remainder of 1 when divided by 9, a remainder of 2 when divided by 8, a remainder of 3 when divided by 7, and a remainder of 4 when divided by 6. What is the product of the sum of the digits of n and the sum of the digits of m? You have time to solve this now, or you could move on. You can pause the video if you want. Okay, let's discuss this first. This problem has three big parts: finding n, finding m, and then finding the product of the sum of the digits of n and the sum of the digits of m. So to find this final answer, we would first have to find n and m. So for n, we're given that n is a positive integer. That is the smallest possible value that satisfies these given conditions, where it has a remainder of 1 when divided by 3, and a remainder of 2 when divided by 5, and so on. We're also given a positive integer m. That is also the smallest possible value that has a remainder of a different set of conditions: 1 when divided by 9, a remainder of 2 when divided by 8, and so on. And then taking all that together, once we find m and we find n, we would find the product of the sum of the digits and the sum of the digits of m. So we would find n and sum up its digits. We would find m, sum up its digits, and multiply those two values together. What do I mean by finding n? Well, we are told that n leaves specific remainders. A positive integer n is the smallest value, a remainder of 1 when divided by 3. But what does this mean? Well, we know that n has a remainder of 1 when divided by 3. So let's say n divided by 3 is equal to some number with a remainder of 1. It could be 10 divided by 3 is equal to 3 with a remainder of 1. N could very well be 10, but we have to also realize that whatever n is has to satisfy for a remainder of 2 when divided by 5, a remainder of 3 when divided by 7, and 10 does not satisfy all of those conditions. But how do we get all of those conditions? Let's see now. So, again, we are told that n leaves specific remainders. You could see it in terms of mod. And what is mod, you may be wondering? Well, mod has to do with remainders. So n mod 3 leaves a remainder of 1. An example being 15 mod 2 is equal to 15 minus 7 times 2, which is 15 minus 14 is 1. Because we can fit 7 2's in there. Therefore, it's finding the remainder of 15 divided by 2. We have so many remainders and so many conditions. How do we sort that all out? Well, first we would see what the conditions are. And if you'll notice, this number, this number, this number, and this number, they are co-prime, meaning they don't have any other multiples or things they have in common other than themselves and 1. This is the key factor in using the Chinese Remainder Theorem. The Chinese Remainder Theorem, it takes many remainder conditions and essentially you put one into the other and you put another condition into another until you get the final condition that satisfies them all. That may sound ambiguous. You may not know what I'm talking about. So let's actually see that in practice. Now, what do these conditions mean? Each statement, like n mod 3 is 1, means that when we divide n by 3, we get a remainder of 1. We can also write this as n is congruent to 1 mod 3, And it also means n is equal to 3a plus 1 for some integer a, because n is a multiple of 3 plus 1. And whatever integer a is, whatever value it is that's an integer, it satisfies for this. Because n can be 10, can be 13, 21. It's a multiple, or 22. It's a multiple of 3 plus 1. So what is modulo? Well, it means remainder after division. For example, 10 mod 3 is 1, 17 mod 5 is 2, because 17 is equal to 5 times 3 plus 2. So how does modulo work with arithmetic? Well, if a is congruent to b mod m, then a plus c is b plus c. A minus c is congruent to b minus c. A times c is congruent to b times c. Now division is trickier because you have to multiply both sides by the modular inverse. I'll explain that while we solve. So, we're tasked with finding the smallest positive integer that satisfies this. I've gone ahead and rewritten it based on the previous logic. This is what the theorem states. Let's use substitution. To begin with, we already know n is congruent to 1 mod 3, which implies n is equal to 3a plus 1 for some integer a. The theorem states we solve by substitution. So substitute n into the second congruence. So 3a plus 1 is congruent to 2 mod 5, because again, 2 mod 5 is our second condition, and we're trying to make them equal. So subtract 1 from both sides, as we've gone over. Then we solve for the inverse of 3 mod 5, because we don't want a coefficient there, we just want a. Or in our case, right now I'm using x, as it's a more familiar number. Try using small values, and we've realized that x2 works because 3 times 2 mod 5 is equal to 1. And we want our coefficient to be 1. And that's what the modular inverse is. So for our case, it's 2. So we multiply both sides. 2 times 3a is congruent to 2 times 1 mod 5. So 6a. Imagine this is congruent. 2 mod 5. Now we would simplify. Because in congruence, we can simplify either sides because mod 5 affects both sides. So this would become a is congruent to 2 mod 5 because 6 mod 5 is just 1. Let's move on. So now we would actually have to do something with our values that we got. This right here. This is what we got. We got a is congruent to 2 mod 5. Essentially, a is a multiple of 5 plus 2, which is how it's written here. And we would substitute our value that we got for a into our original expression, 3a plus 1. And that would lead us to 15b plus 7, or n is congruent to 7 mod 15 if we use the same logic we used here. So now that we know that, any value for b satisfies for both other equations because we've substituted and therefore simplified. Let's continue. So now for the third congruence, because again, all of them have to be combined, essentially. So we would put them side by side. So as you can see, 15c plus 3 is congruent to 3 mod 7 because 3 mod 7 is our third congruence. So what I did is I subtracted 7 from both sides, leaving me with this. And then I simplified the negative 4 because negative 4 mod 7 is simply 3. So we're left with 15c is congruent to 3 mod 7. Moving on, we would reduce the 15. So we used to have 15 there. Well, where did it go? 15 minus 14 is just 1. Because 15 mod 7 is 1. We had a coefficient of 15 in front of the c right here. but we simplified both sides like we did last time. And now we have C is congruent to 3 mod 7, which can be rewritten as such. Then we would plug that back in, as we now know what C is equal to. It's 7D plus 3. We're using different letters to express the different integers that make the previous conditions all satisfy. This is what the theorem states. You just keep substituting and substituting. It's quite fun when you get the hang of it. Okay, so we know this is what our condition so far is, so we would plug C in and get out 105D plus 52. Great, now the final congruence. So we would take our 105D plus 52 and put them against each other. So, subtract 52, which would get us 105D is congruent to negative 48 mod 11, and negative 48 mod 11 is just 7. So 105D is congruent to 7 mod 11. What now? Well, we would reduce the 105 mod 11, which would get us 6. Get it? Because mod, division, it's starting to add up. So 6D is congruent to 7 mod 11. Again, we do not want the coefficient here that hinders our progress, so find the inverse of 6 mod 11 by checking. Boom. X equals 2 works. And why does it work? Because we multiply 2 and 6. And whatever that is, mod 11 leaves us with 1. Which is why it works, because the coefficient ends up as 1. That's why x equals 2 works. Because 6 times 2 is 12, and 12 mod 11 is 1. So 2 is the modular inverse. Let's move on. Oh, right. So we get D is equal to 11E plus 3 because we find out that E is 3 mod 11. It's 3 mod 11 because we multiplied both sides by 2, so this became 14, and 14 mod 11 is 3, which is how we got the 3 here. And we can rewrite it algebraically as D is equal to 11E plus 3. So our final expression for N, we would, again, substitute, put E in, or put D in. So we found out D is 11E plus 3. We put that in, get out 1155E plus 367. What would the smallest possible solution be? Well, if we set E equals to 0, the theorem states that it would just be the smallest value, because if E is 0, that would be 1155E, which is 0, plus 367. So the smallest possible solution is 367. Great, we've gone through N. Now we have to find M. All right, we already found N, and now we have to solve for M. So, here are the conditions for M. M mod 9 is 1, mod 8 is 2, mod 7 is 3, mod 6 is 4. Let's start with the first condition. So, M is congruent to 1 mod 9, which we can rewrite as M is equal to 9A plus 1. Moving on, we substitute that into the second condition. As you can see, right here is where we substituted, and then we subtracted 1 on both sides. Leaving us with 9A is congruent to 1 mod 8. And we can simplify both sides because 9 mod 8 is just 1. So essentially the coefficient becomes 1. So 1A is congruent to 1 mod 8, which we can rewrite like we did to the others as A is equal to 8B plus 1. On to the next condition. So we substitute it back in there because now we know what A is. 8B plus 1, which gets us to N, or M, is equal to 72B plus 10. Okay, third condition. we set up just like so, and we notice that 72 and 10 can be simplified. 72 mod 7, 2. 10 mod 7, 3. Then what we want to do is subtract 3 on both sides, leaving us with 2b is congruent to 0 mod 7. Now you may find yourself in this situation, and because 2 and 7 are coprime, this implies this. And so we get b is congruent to 0 mod 7, which can be rewritten as b is equal to 7c. Why is that? Well, coprime, the inverse of 2 mod 7 is 4, because 2 times 4 is 8, and then 8 mod 7 is 1. And we always want our coefficient to be 1. So let's multiply both sides by 4. We would get 8b is congruent to 4 times 0, which is just 0, mod 7. If you'll notice, we can simplify 8, and it becomes 1. So b is congruent to 0 mod 7, as so, and we can rewrite that as b is equal to 7c, plus 0. Okay. Now we substitute this back in, like previously, and get 504c plus 10. On to the fourth condition. Let's set it up. So 504c plus 10 is equal to 4 mod 6. If you'll notice, 504 mod 6, we can simplify 10 and we can simplify 504. So 504 mod 6 is 0 because 504 divided by 6 has no remainder. So it would be basically 0c plus 10. So 10 is congruent to 4 mod 6. We can simplify. So what's 10 mod 6? That's 4. So essentially it's 4 is equal to 4, which would mean that this side is equal to that side. And so this condition is equal to that condition, so it satisfies for all c. So c is equal to d. You can think of it like that. Now that we have this, which is pretty much unchanged, we can set c right here to 0. Like we did for n, since 0 is the smallest integer, we set it to 0. And that is our smallest positive n, 10. Because 0 plus 10 is 0. Now let's check if it actually works. So 10 mod 9 is in fact 1, 10 mod 8 is 2, 10 mod 7 is 3, and 10 mod 6 is 4. All the conditions satisfy. Great. So what does that mean? Our final answer, we would have to sum the digits and final product. So we found out n is 3, 6, 7, and m is 10. So 3 plus 6 plus 7 is 16. That is the sum of the digits. And then 1 plus 0 is just 1. And then we had to find the product of the sum of the digits. So 16 times 1 is 16. I hope you all learned something, and thank you for joining me in this Chinese Remainder Theorem lecture.